Good morning, car campers. How's everyone doing out there? I am waking up after a great night's sleep, which is a little bit different than 2 nights ago. In a previous video, I showed you how I made my car bed, and I reconfigured it, hoping to add a little bit of storage space, but I got my angles wrong, my incline angle of my bed wrong, and I had a terrible night's sleep because the whole night I felt like my head was down the whole night. So that was bad. So I have actually reconfigured it again, and now I think I have my angles right. But I want to show you something here. Yeah, so I found this neat app on my cell phone, and it's like a bubble level. And so what I can do, let me grab the camera here and spin it around, but I will put the bubble level, on my bed frame and then try to judge where I need to be. And I've found that my incline, if it is somewhere between about 2.5 to about 5.5 degrees slanted toward my feet, that gives me a great night's sleep. So I'm looking at this now, and it's about 4.6. So my incline is about a 4.6 degree angle, and that's perfect. And last night I had a great night's sleep. So if you're building a bed in your car, always think about how you're going to be parking in wherever you're going to park. If you're parking out in the wilderness or if you're parking in a parking lot, think about how your car is going to be slanted in the parking space, and then calculate that into the angle of your bed. And or you can just use a bubble level or a level on your phone, lay it on your bed, and then that'll give you a slope angle. But my preference is somewhere between 2.5 degrees and 5.5 degrees slanted toward my feet. So that's just car camping tip of the day. Okay. It never ceases to amaze me how fortunes can change on a whim. Sometimes for the worse, but sometimes for the better. So about 30 minutes before sunset last night, I had no idea where I was going to park, and I was just kind of hoping for something good, and I found this road which turned into asphalt, turned into a gravel road, turned into a rutty road, and I took the road less traveled, and this is where I found myself. There's my car, that's where I slept, kind of hidden in the sagebrush. I think this is sagebrush, but all night long the moon was not quite full, but almost full last night, and it was illuminating these snow-covered mountains of the high eastern Sierras, and that was my night. But unwittingly, I parked beneath a 700-year-old rhyolitic crater, volcanic crater. So I'm going to explore that today. I did a little bit of research. I walked up to the sign. There's a sign up there, and there's a trail actually around the crater. So I'm going to walk around that today, and then we're all actually going to walk down into the crater to explore some of the geology of a 700-year-old crater. No one around. There's been no one here all night, that I heard anyway. So we have this place to ourselves. All right, let's go exploring. See you in a minute. Just a short distance from my unlikely camping spot last night, in this is it a forest of sagebrush? I don't know. Pretty large sagebrush plants, lots of shrubbery. Get thee to a shrubbery. Wait, get thee to a nunnery. Anyway, but a short distance from my campsite, I saw this information kiosk about Panum Crater. And this is, it says, it's a perfect example of a rhyolitic plug dome volcano. The monocraters of Mono Lake form the youngest mountain range in North America. Rhyolitic volcanic eruptions started here about 40,000 years ago, with the most recent created Panum crater only 650 years ago. So I won't read this entire placard, but it describes the sequence of rhyolitic plug dome events that caused this volcanic crater. I will try not to get too heavy into the geology of this, but this is a rhyolitic plug volcano, and geologists describe rock in different ways. Not only in the composition factor of the rock, what it's actually made of, but how it forms. So if you take the chemical composition, for example, of rhyolite, and you compare that with the chemical composition of granite, basically the same. The difference is granite hardened beneath the surface of the earth, so it cooled very slowly, and the minerals within that material, since it cooled slowly, they were able to crystallize, basically form crystals, versus rhyolite, which is an extrusive rock, meaning that it cooled above the surface of the earth, or at least near the surface of the earth, and it cooled quickly, therefore it didn't have a chance to form crystals. I'm walking up this volcano and I'm out of breath. Oh, this is absolutely fantastic. So my understanding of how Panum volcanic episodes work is this is a rhyolitic volcano. There's a magma chamber deep, deep, deep below the surface of the earth. About 700 years ago, this began erupting, and as the ejecta came out of the volcano, it formed this rim. And I don't know if the camera will pick up the three-dimensionality of this rim, but I'm looking down into a valley, though that's probably 150 to 200 feet deep. And then there's a rim all the way around the center cone of the volcano. So ejecta came out, formed this rim, and there are several episodes of this volcano, so I'm just giving it in very simplistic terms. So forgive me if you're a geologist and actually know how these things work. I would love for you to comment on this video in the description or below the description. But this is rhyolite, and so the ejecta comes out, forms this rim, which kind of forms this valley, and then a central cone eventually builds, and I think there are several episodes of these cones building, and this is just the final one here. But some of the ejecta are, well, some of the ejecta is pumice, and some of it is obsidian. I discovered these two rocks near my campsite. I suspect they are obsidian and pumice. Obsidian and pumice are two forms of volcanic glass that are often found near rhyolitic volcanic eruptions. If we were to do a chemical or spectrographic analysis of these two rocks, we would find they are chemically identical. However, the way in which each formed and their dissimilar cooldown rates after eruption cause them to appear completely different. Let's learn some science by performing a density study out in the field on each of these samples. Okay, so in order to measure the volume of my two samples, I'm going to use my a graduated cylinder here, and this has volume measurements. And what I will do is I will place a quantity of water into this cylinder, and then I will place my sample into the cylinder, and I will measure the difference in volume, subtract it, then I'll measure the difference in volume, and then I will be able to calculate the volume of the sample. My suspected pumice is actually too large to fit comfortably and do a good measurement. So what I'm going to do with my sample here of suspected pumice, move the camera back. I'm just going to hopefully break it in about a half. Okay, that's a good result. That was my hoped for desired effect. And you can see in here all of the very, very fine vesicles within this pumice. Okie doke, so I have my field lab table set up, and it's not ideal. These are definitely not lab conditions. It's more of like a field lab. But what we're going to try to determine, we have a hypothesis, or I have a hypothesis, that I have two samples. Sample 1 is obsidian and sample 2 is pumice. So we're going to set forth trying to prove that my hypothesis is correct. Okay, so the first thing I have done is to make sure that my table is level, because we're going to take some measurements here. So I used my level, the same level that I used to check my bed earlier. I checked my table to make sure it's level. I have a small scale here set to grams, and I have a graduated cylinder here measuring volume of a liquid, and I have poured water to the second graduation here, and that will help me determine my volume of each of my samples. So the first thing I am going to do is I'm going to make a description of my sample. So this is sample 1, and I've taken measurements, and it is about 4 centimeters by 4.5 centimeters in size. So I have written that down. Also, if you take a close look at it, just visually, it's black and it is glassy, and it does have some shiny parts, reflective parts. So I'm going to describe it as vitreous. So a black, glossy, vitreous, glassy appearing substance. Okay, now I'm going to take sample number 1 and place it on the scale, and I'm reading 115.01 grams. So that is its mass, not its weight, but its mass, equals 115.01. And the next thing I'm going to do, and this will be the crux of our experiment here out here in the field. If you notice, the graduations are fairly sizable. The difference between graduation number 2 and graduation number 3 is 118 milliliters. So that's quite a range. So I'm going to have to extrapolate when I place the rock in. I will have to kind of make a guesstimate on the change in volume. But I'm going to do that to the best of my ability. Make sure that it's flat and level. Place my rock gently into the flask and make sure that I do not get my fingers wet, because I don't want to take out any liquid from my flask, from my graduated cylinder. So this is going to be a rough estimate, and I'm going to estimate that the volume changed 40% between graduation number 2 and graduation number 3. Excuse me. So if we take 118, multiply it by 0.4, let's just use the calculator so I don't mess up my calculations. Clear. 118 times 0.4 equals 47.2. So the volume equals 47.2 milliliters, and a milliliter is the same thing as a cubic centimeter. So we'll say cubic centimeter 3, and the mass was weighed in grams. And then what we want to know is our volume, our density. So density equals mass divided by volume. So if we say 115.01 divided by 47.2, let's do this on the calculator. So 115.01 divided by 47.2 equals, that gives us a density. Density equals 2.43 grams per cubic centimeter of the sample. Okay, and I'm going to look up the density of obsidian here. Let's see, density of obsidian is 2.35 and so the known density of obsidian is 2.35 to 2.60 grams per cubic centimeter. Okay, so if we compare our sample, the density of our sample, 2.43 grams per cubic centimeter, if we compare that with the known density of obsidian, which is 2.35 to 2.60, we fall right in between the known values. So we can increase our certainty factor of our sample number 1. We increase it, and we have a pretty based on density, it's pretty likely this is obsidian. All right, let's do the same thing with sample number 2. Okay, so let's take a look at our second sample here, and sample number 2, and I will call this whitish gray in color. It's kind of crumbly when I rub my fingers over it, and it's vesicular, meaning it has a lot of vesicles Looks like a lot of porosity to it, to where a lot of like air holes, very fine air holes, very fine vesicularity. I don't know if that's a word, but I'm going to use it. All right, let's measure the mass of this sample. Right, okay, and the mass is, waiting for my scale, 81.57. Okay, so mass is 81.57. All right, very good, very good. We'll close up the scale here, put that to one side, and now we're going to measure the change in volume of this water in here. Okay, so I have placed my sample number 2 in my graduated cylinder here, and the thing about pumice is it floats because it's less dense than water. So I'm going to just use my pencil and press it down just to where it's just barely below the surface, and I'm going to look here. Okay, and once again I'm going to estimate to the best of my ability. You know, it's not super scientific here, but I'm going to estimate that it is 70% between the second graduation and the third graduation. So 118 times 0.7 gives 106. Let's see. So 106.2. Okay, so its volume equals 106.2 cubic centimeters. And if we do the math, let's see what we get here. Density equals mass times volume, or mass divided by volume. So 81.57 divided by 106.2 equals, so we get 0.768 grams per cubic centimeter. Okay, so the problem with this sample is it's very porous, so some water seeps in, some water doesn't seep in, and plus I'm still working on not a great graduated cylinder here, and I had to estimate it, but we get 0.768 grams per cubic centimeter, which is within a tolerance for a field sample of it being pumice, because pumice, let me look this up. I'm seeing online pumice has a density of anywhere from 0.25 to like 0.80, and this one says 0.64. So we're within the realm of getting a better understanding of what this rock is, and we have a confidence that this second sample is probably pumice, based on our density calculations. All right, so okay, it's not perfect. I realize that we're out in the field and we're dealing with some elements that we can't completely control like we could in the lab, but I hope this gives you some help on how you can take samples of rock and do some experiments, do some calculations and measurements, and determine possibility of what a rock is that you find out in the field. I hope that's helpful. Hope you enjoyed it, and all right.